Video, I'm going to go over essentially stuff that you've already done in Algebra 2 of how to find the zeros of polynomial functions. We're going to talk a little bit about transitioning from the synthetic division goal objective in the last lesson into how to use that to help us find some rational zeros of our polynomials. Essentially, what I view this, and as I try to teach, I'll try to explain, whenever I see any polynomial that I'm trying to solve to figure out what values for x will make it become 0, I always try to factor. Or if it's quadratic, I'm always trying to then complete the square or use the quadratic formula. But what happens is we get these polynomials that have degrees or exponents that are higher than x squared, and so it gives us a little bit of issue if we can't actually factor it. So that's where you'll see the rational root theorem will come into play. We'll use that along with our tool of synthetic division to try to find one rational root. Then usually after that, that leads us into down the road of being able to factor, or we continue using the rational root theorem. So again, I want you to be confident as you're listening to this video and watching it. You have done all of this before. So there's a lot of reading here, but essentially what I want to show you is that if you were to do that same thing that we did in the last lesson with synthetic division, but evaluate this function at 2, you would get what that value is equal to. So what you would do normally without synthetic division is write f of 2 equals 6 times 2 to the 4th power minus 2 cubed minus 15 times 2 squared plus 2 times 2 minus 7. All right, so whatever that is going to be my value when I evaluate it. So if you put 2 in the corner and do 6, negative 1, negative 15, 2, and negative 7, and if we do the synthetic division, all right, then whatever we get at the end, this number, whatever this is, will be what my value is when I plug this into the function. All right, you might be thinking, but Mr. Fraser, can I just use like Desmos to type all that in? Yeah, I totally get it, but I want to show you how we're going to use this understanding to see how we can find some of our roots or zeros, our answers. So bring down the 6. 6 times 2 is 12. That becomes 11. That's 22. That's going to be 7 times 2 is 14. 16 times 2 is 32. So you get 25. So if you were to plug 2 into this function, it would spit out 25. All right. Now, the reason I bring that up is because if you do this, right, and I know we didn't get this when we did it, but we got 25. If we were to get 0, that would tell me that this number right here is what we'd call a root or a 0 of our function. All right, so really when I'm doing this, you're going to see as I get later in this lesson that I'm really focused on hoping to get that remainder is 0. Okay, so let's do that kind of here. I'm going to show that this x plus 2 is a factor of this polynomial by finding, or by showing you with synthetic division, that you get a 0. All right, so I'm going to put negative 2 in the corner. Don't forget to think opposite. 1, negative 6, negative 1, and 30, right? I got that from my polynomial. That's my dividend. So I'm going to do the synthetic division. Bring down the 1, get negative 2. That's going to be negative 8. That's 16. 15 times negative 2 is negative 30, and when you add, you get 0. You should not be surprised by that. It does say in the example to show that x plus 2 is a factor. So we already knew we were supposed to get 0 here, so that's good. So now watch what this does. You write down x plus 2 is your factor times, and as we did in the last lesson, right, we started with x cubed. So if I go 1 less than that, it's going to be 1x squared minus 8x plus 15. Right, so all of that, if I were to multiply it out, gives me my original polynomial of x cubed minus 6x squared minus x plus 30. So now if you wanted to keep going to find the remaining factors, you would hopefully, since this is a quadratic, use our understanding from the last unit where you're going to try to factor. If that doesn't work, complete the square. If that doesn't work, then use the quadratic formula. All right, so if I keep going, I'll go over here. So x plus 2 times x squared minus 8x plus 15. All right, so let's see. Can I think of factors of 15 that add to negative 8? Yes, negative 5 and negative 3. All right, so on this one, I end up getting 3 total roots or zeros, -2, which I already knew, 5, and 3. And that should not surprise you because this is a cubic polynomial, right, that x cubed. So when I graph it, I should touch or cross the x-axis 3 times, hopefully. You'll see later on how that might not always be true. Okay, let's do the same thing here. All right, I'm going to put 2 in the corner this time, right, thinking opposite of x minus 2. So the opposite of -2 is +2. I have 1, 4, -4, and -16, hoping to get, right, 0 at the end. I should, because it's telling me that this is a factor. All right, 1 times 2 is 2. That's 6. 6 times 2 is 12. You get 8. 8 times 2 is 16. Bingo. We get 0. So I have x minus 2 times x squared plus 6x plus 8. I think we can factor that again. Factors of 8 that add to 6, it's going to be x plus 4 and x plus 2. So we end up getting x equals 2, -4, and -2. Now, I'll just be honest with you guys. I know this problem was asking me to do a different process, but if this problem had just said find the zeros of this any way you want, the first thing I would have tried is to factor by grouping, right? So I would have grouped these first two and gone x squared times x plus 4 minus 4 times x plus 4. So I would get x squared minus 4 times x plus 4. That's going to be dots. So x minus 2 times x plus 2. And if you look, right, if you compare this to what we end up getting when we fully factored, you end up getting the same factors, right? So I always try to tell students that, like, I'm teaching you how to do these steps as a way to kind of go about doing this if you cannot use what I view like factoring to be kind of the first thing you should try, or one of the first things you should try. So just letting you know, I don't want you to forget the stuff that we've already kind of talked about. Okay, let's get into kind of the nitty gritty of this lesson, which is we're going to use something called the rational root theorem or the rational zero theorem, which essentially all of this is stating is that if you have a polynomial written in order, right, from your highest exponent to your constant, then you can find the possible rational roots by taking the factors of the constant divided by the factors of the leading coefficient. So I'll show you in this first example, just listing all those. So first I go to the constant, all right, and the fact that it's -4, it's not going to matter because we're going to use plus or minus on all of these numbers. All right, so what are factors of 4? I have plus or minus 1, plus or minus 2, and plus or minus 4. Those are all my factors of 4. Divided by, go to the leading coefficient. All right, I should circle just the leading coefficient. Sorry about that. And what are factors of 2? Plus or minus 1 times plus or minus 2. So when I divide these, I get, here's how I write it. I just write as if you're dividing them all by 1. And then if I take my numbers at the top and divide by 2, I get 1/2. But then I get 2 over 2, which I already have, right? I already have 1. And then 4 over 2, I already have 2. So these right here are what we call our possible rational zeros or possible rational roots. And those are the numbers that I would use first with my synthetic division to see if I could find one of my roots. So we're going to do that right here. So I'm going to do to the side plus or minus, right, factors of 1, which is actually just 1, over plus or minus factors of 2. All right, so I get, I should put my 1 and 2, sorry about that. So here are my possible rational roots. 1 divided by 1 is 1, and 1 divided by 2 is 2. So I'm going to try these first to see if I have any rational zeros or roots. So let's start with 1. So 2, 1, -4, and +1. So if I don't get 0, remember it's not a rational root. So 2 times 1 is 2. That's 3 times 1 is 3. That's going to be -1 times 1 is -1. Ah, look at that. So this one is a rational root. Let's try -1. So I have 2. Now, what I would say is you can go back to the original But if I'm doing this for real, you'll see later on when I'm actually trying to find all of the zeros, even if they're rational or not, I always tell students just use what's remaining. So the fact that we finished with this, and I'll kind of show you what I'm talking about here, right? Essentially, I have x minus 1, right? This was one of my answers, times 2x squared plus 3x minus 1. So if I'm trying to find all of these solutions, I would end up trying to factor or complete the square or use the quadratic formula of this quadratic trinomial, stuff that we did in the previous unit. So I'm going to write down 2, 3, and negative 1. So try to use, just save yourself some time. So 2 times negative 1 is negative 2. That becomes positive 1. That's going to be negative 1. So I don't get 0, right? I didn't get 0. So negative 1 is not in one of my rational zeros. Let's try the fractions now. Positive 1/2. So 2, 3, and negative 1. So I get 2. Half of 2 is 1. That's 4. Half of 4 is 2. So that's going to be positive 1, so not 0, so it doesn't work. And let's try negative 1/2 to finish. So negative half of 2. Let me zoom in a little bit. It's going to be negative 1. Then this is going to be positive 2. That's going to be negative 1, so I don't get 0. So I only have one rational 0 or root, and it was my very first one, right? That positive 1. Oops, sorry. Just that positive 1. So this was my only rational root. So let me show you guys, and you would do this, obviously, if I had to ask you to solve. Do this algebraically, most likely with the quadratic formula. But if I graph 2x cubed plus x squared minus 4x plus 1, let me show you that just because I only found one answer for this doesn't mean that I don't have 3 total solutions. So 2x cubed plus x squared minus 4x plus 1. Okay, so let's show you the one that we found. We found 1, 0. That was our rational 0. But we also have 0.281. That's irrational. And same with negative 1.781. All right, so the rational root theorem was able to find us one of them, but we would have had to use, as I said, I would have used the quadratic formula to find those other two of this highlighted quadratic. All right, let's do it again. Let's try this next one. So using my rational 0 or rational root theorem, I'm going to do plus or minus my constant factors, which 1 times 1 are my only factors, over, this is also 1, so plus or minus 1. So I only have 2 numbers to check, right? That's very simple in terms of my possible rational roots. So I'm trying positive 1 first. Bring down the 1, you get 1, that's negative 4. That's going to be negative 4. That's going to be negative 2. That's negative 2, and you get negative 1. Not 0, so this one is not a possible, or not one of our rational zeros. Let's try negative 1. All right, that's going to be 6. That's 8. Doesn't look good either. Here, you get negative 7. So this tells me I don't have any rational zeros. So if I were to find all 3 of these solutions, they're going to be irrational or maybe even imaginary. I'm not sure. But because I wasn't able to find any here, this is a problem where I would have to use technology like Desmos to find the actual zeros. There's not really a way algebraically I can do this. I can't factor by grouping. I wasn't able to find any rational zeros. So you'd have to end up just graphing it to find those solutions. So x cubed minus 5x squared. So x cubed minus 5x squared. Oops, sorry, didn't mean to open that. Not bad. Minus 5x squared plus 2x plus 1. So plus 2x. Right, so you can see we have 3 solutions. So all of them are real, no imaginary solutions or complex solutions, but all of them are irrational. So again, this is one of those questions where technology would have to be used. All right, so if you want me to write like an answer here, I would say there are no rational zeros. Okay? Okay, so let's get into kind of the whole point of doing the last lesson on synthetic division and now introducing you, or I guess reviewing really, the rational zero or rational root theorem. We're going to be using synthetic division to help us figure out those rational roots or rational zeros. And then from there, you're going to see most likely I'll be using my understanding of solving quadratics to finish. I'm going to find the zeros of this. So 4x cubed minus 3x minus 1 equals 0. The first thing I always tell students is to see if you can factor. You cannot. So then I'm going to use the rational root theorem. So plus or minus factors of negative 1, which is just be 1, over plus or minus factors of 4, which would be 1, 2, and 4. So the numbers I'm going to try, right, are going to be plus or minus 1, plus or minus 1/2, and plus or minus 1/4. Okay, so let's start with positive 1. And this is where I tell students, right, you're hoping that you get 1 on the first one. That we're missing a factor here, so don't forget the placeholder for x squared. I shouldn't say factor, we're missing something in order. So 0x squared, then negative 3 and negative 1. So let's zoom in here, see if we get 0. 4 times 1 is 4, that's 4. 4 times 1 is 4, that's 1. 1 times 1 is 1. Excellent, so we got 1. So how I write this is, I think opposite, so x minus 1 times 4x, and this is going to be 1 less than cubed, so squared, plus 4x plus 1 equals 0. So actually, if you remember, if you can think back to the last test that we took, we actually, for this one, all right, I tried to use slide divide bottoms up. That didn't work for factoring 4x squared plus 4x plus 1. Then I tried to do completing the square. I didn't really want to do that because I'd have a c value that was a fraction. So essentially what I did was I used the quadratic formula to finish this. So if a is 4, b is 4, and c is 1, I'm going to use the quadratic formula to find my other two zeros. So the opposite of b is going to be negative 4 plus or minus the square root of b squared, which is 4 squared minus 4 times a times c, all over 2 times a. So that equals negative 4 plus or minus. That's going to be the square root of 16, and then I think actually the one we had was minus 1. So 16 minus 16 is 0, all over 8. So this is x equals negative 4 over 8, which is going to be equal to negative 1/2. So my solutions here are going to be positive 1 and negative 1/2. And what you might notice is that we only have two answers, right? These are my two solutions. But when we did when you learned about this last year, this highest exponent should tell you the total number of solutions. So that means one of my solutions has what we call a multiplicity of 2, all right? So when I look at this, if I go into my sketch of 4x cubed minus 3x minus 1, so if I go graph it, we should be able to see which one is touching the x-axis but not actually crossing. So 4x cubed minus 3x minus 1. 4x cubed, 4x cubed minus 4x minus 1. Let me just confirm that is right. Nope, 4x cubed minus 3x minus 3x. There we go. All right, and if you look, I'll zoom in. Here is that x equals 1. That was the first one we found. And if you look at our other solution, negative 0.5 or negative 1/2, we are touching the x-axis but coming back. We're not actually crossing it. So this one has a multiplicity of 2. Okay? So in this case, this one right here has a multiplicity of 2. Right? And if you wanted to, what I realized is I thought this was going to be like I did for that last test, but really I should have used slide divide bottoms up here to factor this one. So move the 4 over. So you get x squared plus 4x plus 4. Factors of 4 that add to 4 is 2, right? So x minus 2 squared, but I got to put it over 4. So it's 4x plus 2 squared. All right, so if you solve that, you get x equals -1/2, and that square, this square right here, shows you that multiplicity of 2. So I apologize. I would actually not have done the quadratic formula in this one. All right, let's move forward. Let's make sure we understand the fundamental theorem of algebra. I just mentioned it. It just means that whatever your highest exponent is, that's how many solutions you're expecting to see. All right, so as I said, right, even though I only found 2 answers in this question, because -1/2 has that multiplicity of 2, it really does have, and I know you can't see me, my air quotes of 3 roots. So let's do these last 2 and then we'll be done. Always, 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 guys, right? See if you can factor. It doesn't say that I have to use the rational root or rational zero theorem. So let's see, can we factor this by grouping? Let's see. So I factor out 3x squared times x plus 3 plus 1 times x plus 3. Oh, look at that. We totally can factor this by grouping. All right, so I'm going to have one solution. It's pretty straightforward. X equals -3. But this one is not something I can keep factoring. So I'm going to set it equal to 0. Move that 1 over. And then divide by 3. And what I notice is to get this to be just x, I'm going to have to take the square root of both sides. And that's going to leave me with a square root of a negative. So these 2 solutions are going to be complex or imaginary. They're going to have the letter I. So this is the square root of -1 over the square root of 3, which is equal to I over the square root of 3. I'm going to clean that up just a little bit and write that as the square root of 3 over 3 times I. And I forgot, so hopefully you don't, that I must include my plus or minus because I am taking the square root of both sides. So there's 2 solutions. And this one right here is going to give me x equals -3. So there's my third solution. If I were to go and find the graph of this, right, I'm not expecting to see 3 times crossing the x-axis because 2 of my solutions, 2 of my zeros, were complex numbers or imaginary numbers. So I should only see 1 where it crosses the x-axis at x equals -3. So 3x cubed plus 9x squared plus x plus 3 plus x. And sure enough, when I look at this, you can see, too far, we'll do this. You can see we only cross the x-axis at 1 of them, and we don't have another time that we touch or cross the x-axis. So that's why it looks like there's only 1 solution, but we had 2 that were complex with that letter I. Okay, let's do one more, and then you guys can try some of these on your own. Unfortunately, if I try to factor by grouping here, right, if I write 2x cubed plus 5x squared minus 11x plus 4, I'm not going to be able to factor by grouping. So what I'm going to do instead is do my rational zeros, which is plus or minus factors of the constant, so 1, 2, and 4, all over factors of the leading coefficient to give me plus or minus 1, plus or minus 2, plus or minus 4, and then plus or minus 1/2. All right, so let's try number 1. And let's put 2, 5, -11, and 4. Bring down the 2. 2 times 1 is 2. You get 7. That's 7. That's -4. That's -4. And look at that, we get 0. So it worked out nicely that the very first one that we got was one of our roots. So think opposite when you write the factor. Then 2x, right, 1 less than cubed is going to be squared, plus 7x minus 4 equals 0. Let's try to factor this quadratic trinomial. So try to imagine that we're, backing up 1 unit. So 2x squared plus 7x minus 4. Let's do slide divide bottoms up. So x squared plus 7x minus 8. So I need factors of -8 that add to 7. That's going to be plus 8 and minus 1. Put it over the number we slid, and you get x plus 4 and 2x minus 1. Bring down this factor, right, because that one was the very first one we found. So we can find our 3 solutions. 1, -4, and +1/2. All right, so those are our 3 zeros. So when I graph this one, I'm expecting to see 3 different times that we cross the x-axis because all 3 of my zeros were actually integers, or in this case, rational numbers with that fraction. So I have 2x cubed plus 5x squared minus 11x plus 4. All right, and sure enough, let me just do this real quick. Make it a little easier to see. There we go. So you have -4, 1, and 1/2. All right, so there's my 3 solutions. All right, so hopefully you guys can try some of these practice problems, and then don't forget to come see me if you have any questions. Good luck.